Okay, good morning to all of you. You can never trust the weather here. In the morning when I woke up, it was sunny. I came with this, and now? Okay, so a final bit in in clustering. Then I promise you, we close clustering. Okay. Can you hear me with the microphone? Okay. So yesterday in the motivation, okay. So the motivation from going beyond k-mean to some other algorithms was that k-mean was expert and k-mean deals really well with Euclidean distances when we have a spherical clusters. This means there is no correlation between the data inside that cluster. But the problem comes when we have correlation between the data, so the cluster then is no more spherical. It can take any weird shape. Okay? But particularly we can say, okay, it can take elliptical shape. So there is correlation, then k-mean cannot help us. So we have to find another way to take into account this correlation between these points. So we have a new model or a new algorithm that can deal with those correlations. We call them T-clustering. Okay? And the idea here is the T-cluster trims some of the far values in your data, which we could consider as outliers. Okay? And we also know when we were studying k-mean, we said if we are having outliers in k-mean, k-mean goes crazy. So one of the benefit while using T-clustering, it's robust. It's robust to outliers. Okay, so we remove those extra points, those outliers. And the other benefit is now we can take into account also correlations. Okay, so the same thing, which I'm just repeating from yesterday to fresh your memory. And then we have the function in MATLAB, which is T-cluster. You have these arguments, x your data, k the number of clusters you want to, alpha is how many points you wanted to trim, and then we have the refactor, which is a fourth option where you can control the covariance of your cluster, basically the shape of your cluster. Okay, so then we saw an example yesterday which was we want to trim alpha 0.10. This means that if we have total number of points n equal to 100, so we trim 10 observations from our data. So 100 minus 10, we have 90 points in our data that we need to cluster. Okay, so the outliers or the contamination we had in our data, we trimmed those. And if we trim those, we can have these kind of clear, clean, solid structures, clusters. The 90, sorry. It depends on you. You can choose 0.05, 0.01, 0.10, but usually we choose 0.10. Okay, so now the last option was in this function, which is refactor, to control the shape of your cluster, to control its variance. Okay, so it is like the ratio of the smallest and the maximum eigenvalue of the covariance matrix. Okay, so basically the eigenvalues gives you how to control your variance in the data. Okay, so if the covariance terms, the eigenvalues are 0, this means the variance is constant. If they are having some values, the eigenvalues are having some value, this means there is some covariance in your data. Okay, and if this value is equal to 1, this means that the eigenvalues are the same and you have the variance is constant. Again, you fall into the spherical cluster. And if its value is larger, this ratio is larger, then we have an elliptical or elongated cluster. Okay. Yes.
The value that lambda represents are the sum that we.
Which values?
This
one. Yeah. This ratio.
Yeah. Lambda max and lambda.
Yes. You sum the eigenvalues in the covariance matrix. Okay. So we can have two shapes like this. If this factor is equal to 1, so we have a spherical cluster. If this is larger, we can have this elongated kind of structures. Okay. And meaning of this, if this factor is equal to 1, so we are again in the spherical clustering, meaning that for T cluster, if this factor is equal to 1 is a special case, and that special case is k-mean. Okay. Now let's look to some of the examples. So for instance, you have exercise in your book which is 2.9. We want to simulate two bivariate normal groups. So we create them. The first group is, we have number of points 300 and it's around 2 and 3 points. Group 2 has these number of points and is situated at these position at the x and y coordinate. And both groups are having the same covariance. Okay, so they are having the off diagonal terms that represents covariance, so the covariance is the same. Now the task of the exercise is to plot, just have a scatter plot to look to your data, and then notice what effect covariance has on your clusters. And then we try on both algorithms. We run both algorithms, k-means and T clustering, so we can visually see now what's the difference here with real data. Okay, but before going into the MATLAB or before going to coding, just to a kind of intuition. If you look to the covariance matrix, what we have, the off diagonal terms are non-zeros, so they're having values. If they are non-zero, this means there is covariance, some kind of, okay, a factor. If these values were 0, this means we don't have any covariance between them. Okay. So if there is covariance, this means we are in the case of the points are correlated to each other. So if the points inside a cluster are correlated to each other, we don't have then a spherical cluster. Now we have elliptical or tilted or any other shape of cluster. Okay, because of what? These covariances. Okay, so this is before going into the code, we have this idea. Okay, if the covariance is equal to 0, we have this shape, and if the points are correlated, we are now in this scenario. Okay, and in MATLAB, okay, we have the covariance, which was this matrix. The number of points is 300 in the first group, which is around 2, 3, and then you create these random numbers. Okay, around the mean points, the variance, and number of points. So this is the first group. And similarly, we have the second group. Okay. And then we take points. So group 1 is from point number 1 to 300 to N1. Okay. And we label it with 1. In group 2, so we start now from 301. So N1 is 300. So 300, the starting point is 300 up to, N2 is 200. So 300 to 500. Okay? Yeah? So the first group we label it 1, the second group we label it 2. Then we combine them and we plot. Okay? So this is the first idea. Yes? Okay. So as we were mentioning before, these covariances has some value. But if you want to try, and if you put the value of these covariances equal to 0, so here it was 1.5, 1.5, we had a correlation. But if these values are 0, then we don't have correlation between the points. If no correlation, then we have a spherical cluster. Okay? Now, to run on both algorithms the data, k-mean and t-clustering. So in this exercise, we don't want to trim anything. We don't want to trim data. So alpha is equal to 0. We want to have 2 clusters, so k is equal to 2. And C, the factor, the ratio between lambda max and lambda min, that ratio was what? To control the covariance, so we fix it, yes, it's greater than 1. Yep. Okay, so we choose its value equal to 10. And then we run both the algorithms. Okay, so tk means and plot them, and t-cluster with this function. Is it clear? You with me? I'm losing you? No. Okay.
So if the 1 is the group number,
Here?
no. It's right in the 1.
Here?
Then the other. Rest of defect.
It has to do with the plotting. Okay. Here we have 1 for a kind of label for group 1, and this is for group 2. Okay, if you see now, so the plots are like this. On the, for you this is, yeah, Habib. No, for you this is, right? Okay. This one, on the left, for you is the left also. Yeah? Okay. This is the left for you, right?
Yeah.
Okay. So, here we have k-mean. Okay? We applied k-mean cluster here and here t-clustering. So now we can see the idea of k-mean was what? Just a spherical structures. So it's fooling us. You know, it's creating clusters which is not correct. Okay, so it okay, this is one cluster, this is another cluster, this is another cluster, this is another cluster. Or it says, okay, this is one cluster, spherical one, and this is another cluster. But in reality, we just have 2 clusters, and those are elliptical, because we saw also from the data matrix. Yeah? So, we have this elliptical for the first group and this for the second group. Okay? So T cluster has divided the data correctly.
How did we know that it's elliptical from the group?
Because we saw from the matrix we have some covariance
Okay.
in your data point. So if there is covariance, this means there is a relation between them. Then it take the shape of elliptical. Then you cannot apply the Euclidean distance. When you apply the Euclidean distance, you will have a spherical structure. But in this case, no. So we have elliptical. Okay, is it clear? The difference is clear. Okay. Now, okay, we did this. Okay. Now, so why T cluster succeed here? Why it succeed? Because we can play with two things here. The shape of our cluster, because we can, based on the C value, we can increase or decrease the variance covariance. Okay. And also the other thing here, we can apply the T clustering. So we explored the covariances, we explored the shape of elliptical clustering. Okay. So that's why T clusters succeed respect to k-means. Okay. Similarly, if we consider the value of C equal to 1, that factor, if that ratio lambda max divided by lambda mean, where is it? Okay, if this value is equal to 1, C equal to 1, we said before, this is again a spherical structure, spherical cluster. Okay, so which is again a special case. Yeah. Okay. So if C is equal to 1 in T clustering, this means that it behaves the same way like k-mean. Okay? Now, if you want to try it, try this at home. So alpha is equal to 0 again, but we choose in this time C equal to 1. Okay? So it's the same. It resembles the k-mean. Okay, no problem. Now, let's see another example. Exercise 2.10 in your book. Now, we create two groups. Group number 1, this way. Covariance is like this. Group number 2, this way. So we have these two groups. Now we want to add some data, some contaminated data to these two groups. So we have group 1, we have group 2, and then we add some random data in between them. Okay? Which is this. So now, if we use the classical mean algorithm, what will happen? And if we use T cluster, or if we use k-means with trimming. So in FSDA, in the toolbox of FSDA, you have the k-mean algorithm with the possibility to use trimming. Okay? So with this data, we will try to apply these two algorithms. K-mean, the classic one, which is good for spherical clustering. And then we use k-mean with trimming. And we see how well it separates the two original groups from the third group, which is the contaminated group. Okay? Are you with me? Yeah. Okay, so the classical is this one. Okay, you say k equal to 3, we have 3 clusters, no trimming, alpha equal to 0. But with the trimming, then the alpha is something like this, takes this shape. N3, number of points of the third group, the contaminated group, divided by group 1, group 2. Okay? So we want to exclude this group, which is kind of a fake cluster. So this is the intuition. Idea is this: we have one group, one cluster, we have another cluster, and we have added this contaminated data.
But to do that, you have to know it before. Which one is the contaminated?
Yes, and that's how we are adding. So we know it. You are correct. So the idea is this, to exclude this from the two groups, okay? From the original groups, this fake data, let's exclude it. So we do some coding. Generate the first group, around 2, 3, the covariance matrix is this. We have N1 equal to 300 units, and these are random points, so we generate it like this. This is the second group, and here we add the third, which is the contaminated data, okay? Then we combine all of them and we apply k-means. So for k-means with trimming, we use this kind of technique. So the contaminated group, yes?
What's the point of adding contaminating data and then removing?
Just for fun. Just to show you how it works. If we use trimming and if we don't use trimming. Okay. So now we are adding it, but maybe in real situation you have a data set, there is some outliers, there is some contaminated data, and you figure it out, now you want to remove it. So this way we can remove it. Okay? We can see. So here what we did this step, which is this one for alpha, okay? N3 divided by N1 plus N2. And then we use the two algorithms, k-mean, the classic one, and k-mean with trimming, okay? So the classical one, we use alpha equal to 0, correct? And in the trimming we have now this for alpha. Instead of alpha we have this. And we plot. Now, when we don't have trimming, you see, the red one is the contaminated data, okay? This is the case of alpha equal to 0, the classic k-mean. And this is the case of alpha k-mean with trimming. In the case of alpha equal to 0.10, okay? So in this case, no trimming, alpha equal to 0, the contaminated part, if you closely look, it's kind of swallowing the group 1, okay? So it's swallowing some of the points and it's taking them. That's the problem of contaminated data. It can distort your clustering, okay? But instead, if you look here, we have done some trimming. Group 1 is very clear, group 2 is very clear, and the contaminated data is very clear. Notice also for labeling in these graphs, maybe, I don't know, it's very difficult to see, but here on the labels, when you plot these on MATLAB, if k-mean is without trimming, you will see the labels as 1, 2, 3, okay? And if it's with trimming, you will see the labels at 0, 1, 2, okay? It's the only difference. Okay, that's it, and that's the end of clustering. Now, we move to something else, and which is, you need a break, 5 minutes, now or after? Okay. So, now the idea is to set a stage for logistic regression and those kind of things, okay? And of course, those are, till now, what we were studying. unsupervised classification, unsupervised learning, unsupervised clustering, right? Why those were called unsupervised? Because we don't have labels, we don't know the data, we have no information. Now we are moving to supervised classification, supervised clustering. Okay? And in supervised, we know the output, we have labels. So we have input data, we have output data, so we have labels. Okay? Now, if you remember in PCA, what usually we used to do is okay, in PCA, if you remember, we had let's say some points. Okay, and we by choice draw them to have some direction. So this is PCA. In PCA, we try to find the mean of the data, okay, the average of the data, and we get something like this, the average of the data. And then we subtract the average of the data to get a new component, something like this. We have a new component around the mean, the data. So this is first principal component, then we subtract again, we have the second principal component, the third principal component, the nth principal component, and we move like this. Okay? But in PCA we ask this question, do I really need all of, yes? Yeah. So in PCA we ask this question, do we really need all those components? We said no, maybe majority of those components are redundant. They don't give us meaningful values, okay? So we keep maybe 2, 3, 4, 5 principal components and we throw the rest, okay? Those are not adding meaningful values to us, okay? So PCA operates on the data itself, and most importantly, it's unsupervised method, okay? But if we have a technique, if we have a method that can help us in dimensional reduction, why we need something else? Why we need another method like linear discriminant analysis? If we see some time, but majority of the time, the data is very complicated. Okay? Each application is different from each other. So in reality, okay, the theory is good. We know the theory, but sometimes, okay, when you have a real problem, maybe for someone say, okay, this is the theory, and they're praising about this theory, this is really good theory, do this. But when you apply this theory to your real problem, maybe it's not working for you. Okay? So if it's not working for you, then we need some alternatives. We need alternatives, methods. And it's good to have, for each problem, maybe 2, 3 different methods in your repository. Okay? So if one is not working, you try the other one, okay? So the basic idea is this, but, okay, moving on. So this is the next method we are trying to explore, and which is LDA, linear discriminant analysis, which is completely different from PCA, okay? PCA is what is unsupervised. It's unsupervised and it's linear. it's unsupervised, and it's linear method. Okay. On the other side, we have LDA. If I try to map the same data, if I try to make the same data now, what LDA does? It tries to make or tries to project this data into some other coordinates. Okay? It's the same data, but it tries to project it into some other data, some other coordinates. For example, it starts something like this. Okay? It projects this data to that axis. Okay? Kind of projection. And similarly, it tries to project the data here on the other axis. Okay? Now the question LDA asks is, which axis gives me more so it's asked the question, which axis gives me more discrimination between the data, between this data, this axis or this axis, okay? So this means LDA operates on features, operates on subspace. So this is subspace 1, this is subspace 2. Okay? And these are kind of features for us. So then we look into these axes and we say, okay, can we see here a valley? Or can we see here a valley? You know valley? A space between two mountains, high region. Very close to K2, and a big mountain, and then another big mountain. In between there. So can we see a valley here? Can we see a valley here? If we see a clear valley, this means there is a discrimination, okay, between this part of the data and between this part of the data, okay? But now, okay, I'm getting a new method, which is LDA, but it's still linear, it's not non-linear. It's still linear, but what's the key point here now? It's still linear. Yes. It's, who said this? How do you like? So it's supervised learning now. Okay? It's the key difference now. So here, PCA says, okay, give me your data. You give your data to PCA. What PCA does, do the dimensional reduction, gives you principal component 1, 2, 3, and so on. You say, okay, I just need to keep the first 3 principal components. I don't want to work with 2,000 features. I don't want to work with 2,000 principal component analysis. So you just keep 3. That is what PCA is doing as a dimension reduction. But now here, we have the same. We are doing dimensional reduction, but we are doing also something else. Okay? We are doing dimensional reduction, but we also have classes. and now. So this is important distinction now. When you studied PCA, you never talked about classes. This is the first time we pronounce the word class. Okay? Because in PCA, we don't know nothing about the data. We don't know what's inside the data, what's the structure inside the data, what's the classification there. That's why it is unsupervised learning. But when we move to supervised learning, now we talk about classes. Okay? So we can now divide the data into classes based on what? Based on the labels. So PCA said to you, okay, give me your data, I do for you dimensionality reduction, and I give you back the data. Now, it's your job. What you want to do. You want to classify? Classify. Do you want to do whatever you want to do? For me, I did for you dimensionality reduction. That's it. So PCA tells you, okay, I don't care about your Excel file. The last column of your Excel file, what's the labels there? What's the output there? I don't care about those labels, okay? But instead, LDA is a bit, he wants to do something more, okay? He said, okay, I did for you dimensionality reduction, but now I can also classify for you the data, okay? So this is the idea. So how we can formulate LDA? It's say, okay, we say to LDA, go find the line, go and find the line that maximize this discrimination between the classes, okay? So we say to it, go find the line that maximize the discrimination between the two classes. And this is what we do every time in majority, like 80% of the time we do this in artificial intelligence. We want to discriminate between two classes. This is what neural networks do. This is what we did with K-mean. So majority of the algorithms do this kind of thing, to discriminate between two things, okay? So, what we have to find the best line that discriminate between these two. Yes? Question? So we need the best line that discriminate between these two classes. Okay? So let's say if we have samples and one sample that belongs to class 1, and then we have two samples that belongs to class 2. So we have data, it's kind of random data, but we say some of the samples which are N1, those belongs to class 1, some of the samples are here which belongs to class 2. Okay? Now, we want to remove this. So here we are in supervised learning. Now you tell me what's the difference? What's the difference here? The goal is to find that line that discriminate between them. But why? Yes.
It does the discrimination, but
it's kind of the same way in PCA, but then it does something else.
So
We will go
that's
to
the
the theory now.
um,
Again, mathematical derivations. But this is just a general intuition today.
because I thought that it has to search for the best maximization. It has to maximize the discrimination, right?
Yes.
So in order to do that, it has to look for the best line, which is the second one.
Yes.
Where is the dimension reduction? We don't have to remove any data. Like we're just plotting a line between data.
Which is really good
Same
point.
thing as clustering.
Yes. No, it's really good point because okay, here now really we are not really working on the real data. So the dimensionality reduction part is we are not working on the real data, but we are projecting the data. So once we project the data, that's the part of reduction. Okay? What we are doing here is this. To find the best discrimination line, what we do here is to project these. So we project. Okay. But why I draw here just dot points and we're here plus?
Different classes.
Hmm?
Different classes.
Okay. So here we project it, and that's the part we do
We project only on the x-axis.
on the axis. We can explore more axes depending on if we want to, like the previous example. So we have to explore which way we can have more discrimination. Okay?
Yeah.
Okay. So before, till now, when we used to draw any plot, any figure, we used to draw with some dot points. Okay. But now we are in supervised learning. We know the classes, we know the labels. Okay. When we know the labels, okay, dot, the other classes represented with cross, with point, with plus, with arrows, whatever we want, because we know the label. So this distinction is important. Okay. And why this is important? When you have a problem, you should know, shall I use PCA or shall I use LDA? Okay? Now, if you can see here, you can draw this line. Okay. Should be straight. Okay? So now we can draw this line. And this is the line we don't know. This is the line we want to explore. This is the line which can give us the maximum discrimination. That can maximize this discrimination. We don't know this line. And this is how we have to find this line. Now here is another distinction. If this is a line, and if these are lines, then why we are doing this? Because a line here and a line there. What's the difference? So the difference is, in PCA, your line, okay, this is your component. You can go this way, you can go here, you can go this way. You can basically go up, down, as you want. But in LDA, if we see, this unknown line passes are started from the origin. Okay? Now we are not free. So we are here from the origin. We can just do these things. This and this. Okay?
But this limits its potential, no?
Hmm?
It limits its potential. For example, as you draw here, it could never classify the data perfectly.
Which data?
This as you draw.
It did classify. Look, this is class 1.
Yes,
This
but you
is class 2.
said that
You
the
can
line-
see this difference, this like between, I don't know, Africa and Brazil.
But you said the line has to go from the origin.
Huh?
You said that the line has to go from the origin.
Yes.
Yes. So it can never distinguish between the two
I mean, how?
If the
You
line
say, you
crosses-
meaning if this line is like this?
I mean, the line has to go from the origin, right? So, it classifies between, like, classes under the line and classes above the line, no?
No.
It doesn't work like that.
We have to start from the origin, and we have these projections.
Uh-huh.
The difference is here. This is the discrimination. Okay? Because you know the data is very, very, very complex. We don't know nothing about the data. So each time we kind of design an algorithm because we don't see the data. We say to the algorithm, go inside the data and explore for us. And
Here we know about the data.
sorry?
But here we know about the
Yes,
data.
in this, we know about the data, but we cannot see it. I mean, we have to plot it, we have to explore it, we have to do some kind of data analysis, but you cannot go inside here and see, okay, where is the data? You have to design algorithm for this, right? Okay, let's do 5 minutes break. Yes. Sì.
Vabbè, quindi in questi grafici noi stiamo mettere su interno solo due variabili, dove ci stiamo plottando in due dimensioni e per capire cioè anche quel video della DCA, nel senso stiamo riducendo da due a una variabile, nella realtà avremmo, non so, i 7, 8, 9, 200 variabili e poi lo possiamo vedere subito. Ma volevo chiedere, cioè questa è la linea della maggior variabilità. Cioè se usa questa linea.
Chiede la discriminazione che dice tra questo alla fine vediamo un altro grafico sì, so quindi l'idea è lo stessa che avevamo prima.
Decido quella variabile 1 x quella che c'è la maggior variabilità. Non ho bisogno di questa, cioè sto già proiettando per distanza, cioè possiamo simile a questa sì.
Che in realtà questa qui è una cosa di partenza. Il costo di partenza vuol dire che se tu progetti questi, tu progetti direttamente solo questo, però quindi da quella cosa che quando si lontana da questo punto di vista, questo non si diventa
qua.
Sì, in realtà qui, ma qui per noi è un po' difficile da vedere, ciò quindi noi le riposiamo qui e qui ad esempio, ok, vediamo quello dopo, qui se magari abbiamo uno qui, allora uno qui, e vediamo quelli dopo.
Sì, quindi in realtà uno è quello qui, qua per esempio sta questa però
Sì, sì, perché ok, qui abbiamo la data.
cioè come se fosse la PC1 questa.
Esatto. Quindi qui abbiamo la data, questa data, questo però noi vogliamo fare qualcosa molto più vicina, molto più corretta al nostro però in realtà è molto complesso. Questo è non so, per prendere una piccola idea, ma se abbiamo 10
No, cioè è tutto il concetto della riduzione della dimensionalità, bisogna perdere
però
dopo una PCA dove invece di trovare una dimensione latente, più dimensioni latenti ortogonali e fare un cambio di base, troviamo direttamente una dimensione che segua la base canonica e segua le variabili originali, cioè invece di creare delle nuove dimensioni seguo quelle che abbiamo già, seguo le variabili che abbiamo.
La cosa era qui, e questa qui è 130 anni prima. Questo qui è nuovo, 15, 17 anni. Ok, la maggior parte delle persone usano quello, perché hanno più confidenza che già da 100 anni che sta funzionando. Questo qui è un po' nuovo, però la distinction è quello lì, che questo supervised, quello lì è supervised. Ma ok, le cose non sono, sono la matematica, no? Se vogliamo, questo qui, la variabilità tra questi due deve essere massima. Ok, quella variabilità chi ti dà? Questa linea ti dà. Ok? Su base di questa linea dividiamo la variabilità tra questi e ok?
डिस्क्रिमिनेशन कैसे करेंगे
या भी एक और फिगर देखेंगे उसमें, लेकिन असल में ये बहुत कॉम्प्लेक्स है। तो अब दो वेरिएबल्स हैं हमारे साथ, 10, 100, 300, 400, 100, फिर क्या होगा? So, वही पुराना वाला एरिया है जो क्लस्टरिंग का था कि दो क्लस्टर के बीच हमें वेरिएंस ज़्यादा चाहिए, डिस्क्रिमिनेशन ज़्यादा चाहिए, और विद इन अ क्लस्टर हमें कम चाहिए। वही आइडिया, ये वही लाइन है जो एक किस्म का ये देखता है कि ये कितनी दूर है, ये कितनी नज़दीक है। तो ये वही लाइन है जो हमें देता है वो डिस्क्रिमिनेशन दो क्लस्टर्स के बीच। वही जो लाइन
कैलकुलेट करेंगे तो थोड़ा सा ऐसे भी कर सकते हैं।
हाँ, वो कर्व जा सकता है, वो फिर है कोऑर्डिनेट सिस्टम।
ऐसा नहीं होगा कि कट कर दो, इसको भी कट कर दो, ये इसी ये जो वेरिएबल्स होती हैं
हाँ, अगर आप जाएंगे हाई डायमेंशन में, फर्ज करें आपके पास 10 क्लस्टर्स हैं, तो हाँ, चली जाएगा, क्लासिफिकेशन जाएगा, वो फिर बहुत
फिर हम डायमेंशन रिडक्शन,
हाँ, तो ये सबका ये प्रोजेक्शन जो है वो डायमेंशन रिडक्शन जो PCA में हम करते थे वो बड़ा हेक्टिक प्रोसेस है। लेकिन आइडिया वही सेम आइडिया सुपरवाइज है, एक पास लेवल्स हैं, तो हमारी कोशिश ये है कि इन दोनों उनका पास ज़्यादा हो, विजिट पास कम हो, और वो कौन हमें मिलता है वो लाइन जो हम नहीं जानते पहले से कैलकुलेशन तरीके से हमें वही लाइन
video on Arabic. I don't know if I have the chance to do it or not because I am working on it and I have some modification.
If you have time, do it.
Okay, then tell when I.
No problem.
Oh, it's
Just
okay.
if you want to do and if you have
Yeah, I
time,
am working on it and still I have some modification,
take your time.
Yeah, I want to make it like simple and just like the other versions.
Yeah, simple. Do it
Yeah,
simple. Don't go in too much details or don't, because
No, just
it's not something,
introduce
I
the
don't want
FSDA.
your time to be, your energy to be vested on something like this. Because just for, look to the other video.
Yeah, I am
Okay.
doing like
Yes,
the
it's
same.
more or less the same thing, but just
Yeah.
maybe with different presentation
Yeah,
type
of course,
and
yeah, but I mean like the same things they do, the simple one, just introduce the FSDA.
yes.
Okay, thank you.
Okay, so we are back. Okay, so this was just a general intuition, and so we have a kind of picture in our mind what we are doing. Okay, and here, okay, the idea is to LDA. We are not going too much in detail, but just kind of to skim it. Okay, to have an idea, because this is just the basic of supervised classification. And the idea is just to set a stage for logistic regression, which usually often used in practice more. Okay? So, we have the classification problem now. And the problem is, suppose we observe a vector of predictors. We have these values, these endpoints, which is x equal to from x1 to xp. And we want to assign these points to some group, to some class. So these points, how many points we are belongs to which group. So for instance, example could be, we have a patient, either is healthy or diseased, or so many other examples like email, spam, not spam. Okay, so the idea is we have data and we want to classify them into 2 classes, 3 classes, 4 classes, 5 classes. Okay, so that's our problem, the classification problem. If you remember from yesterday when we were dealing with the mixture models, we presented this idea of probability, the posterior probability for classification. Okay, we use the same idea here. So we have unit number x, which is capital X belongs to x, any x, and we want to know its probability, how probable it is to be in this group, in group K. Okay, so this is the posterior probability. We want to find this probability for each of our data points, and we assign these values of x to the class having the largest or highest probability. So for each point we have its posterior probability. x1 belongs to group 1, group 2, group 3 or group 4. we find this probability. We say, for instance, x1 has a high probability to be in group 3. So we assign x1 to group 3. Yeah? And here is the genius guy, Bayes' rule. We use Bayes' rule for this, in which is for each class we calculate this probability, which is the density, okay, the density of x in class J. So how much x is in that group, so how is its distribution, the density, okay, and then the prior probability, how probable is this x in that particular group, okay, and that probability for all those classes will be sum equal to 1. Okay, so probability of 1, 2, 3, at the end it's a PDF, sum to 1. Yep.
Can you visualize as a, on the board? Couldn't imagine.
What?
I mean the probability.
This probability?
Draw something.
Draw something.
I don't know.
What?
Sorry.
I don't know what to draw. Help me.
I don't know.
You don't know. I don't know. It's a classification problem now.
What do you want me to draw?
What do I?
What do you want me to draw?
Yes.
I want to do the probability thing.
And the example is that of the
An example,
false positive
control example.
of the COVID test.
Okay. What do you want me to draw?
Some graphs. An example, I don't know. How can I do it?
Okay. You have some points here. Okay. Okay. We have these points. Now we want to know the probability. This is, let's say, something like this, the whole data set. But we don't know these classes, which classes they belong to. Now I draw it like this, but maybe they're random, right? So for each point, what we want to do, this is, let's say, class number, group number 1, group number 2, group number 3, okay? Now, we have a new point, like you, the outlier. Okay? We have this new point now. Now we have to decide which class it should go. To here, or to here. Okay? So, with this point, for this point, we calculate the probability. If this belongs to group 1, so this is X probability. Now you know. Brilliant. Well, you said to me to draw.
I can't visualize it in my
Is
brain.
it belong to group G based on X, okay? And then we use the Bayes rules, okay, to find, okay, how is the density here and how probable these points are here, okay? And so already we have the posterior probability for each of these points. We have the posterior probability for each of these points. We have the posterior probability for each of these points. And now we calculate this one. Okay? So once we have information about this, information about this, information about this, we know this point, if its probability or the number of occurrence is similar to this, we assign to this, this, or this. What? Okay. Where we are. Okay, so we have the density, which is fx of x, and the prior probability, okay, divided by the summation of the density multiplied by the probability. This is general base rule, okay, we studied this in school. Now which school again, I don't know. So in the numerator we have this, okay, and so this is how common, this tells you how common this new value is to this class, or how common values we have in this class, okay. And density tells you how typical x is. Is it confusing again? Am I losing you?
No, I'm good.
So in the denominator we add all those quantity, we sum them. So it's a kind of normalization, okay? So in the numerator we have the density for each point, we have its prior probability for each point, then we divide by this summation to kind of normalize it, okay? So the idea is the classification here depends on two things. Classification for a new point depends on two things. Its density, okay, how well this class is defined, and second, the prior probability. So if we have these two things, we can make a good classification, okay. And then we have different ways to do this. So we can have different class densities. We can have linear discriminant analysis, which is this one. We find the linear line, and that linear line discriminate between the classes. But then we can have quadratic discriminant analysis, where we can get like curve-shaped clusters, okay, curve-shaped groups. Before in the example we saw we had the linear line. That line we were not knowing that line in advance. In quadratic we can have curve. So this density, we can have mixtures of Gaussians, we can have the non-parametric density estimation, or we can have naive Bayes, okay. So it depends on what we are doing. So we should ask which model shall I use, or which distribution shall I use, which density I shall use, okay, or which one shall I assume is more correct. So we have the Gaussian assumption for LDA, and that assumption is we assume that each class density is multivariate Gaussian. For each class in our data set is multivariate Gaussian density, and multivariate Gaussian density is like this. You know it?
No.
Me neither. So we have this now, where it is distributed with mean mu k and covariance sigma k. Okay? So we assume that each class shall have this kind of distribution. That's the assumption. When we want to classify, we assume that each class we are gonna to find shall have a distribution like this. Okay? So where mu k is the mean, so it's the center of the density, and covariance is how spread your class is what's the shape of your classes, okay? So we can have both things. Where my class is located, how we know from the mean, okay? From the mean of that class. Once we know the mean of the class, we know where this class is located in my data set, okay? And with the covariance, I shall know, is my class narrow or is wider, what's the shape.
Based on shape, we decide which method we are going to apply. Like LDA,
To which one to assume. If you assume this one and it's best explain your data, you say okay. But if you see something very strange, you change to another, maybe to naive base, and then you try which one gives you better results. Okay, okay. This is the exponential term you mentioned yesterday. Mahala nobis distance. Okay. Now here we can use this distance. Why? Because now we have correlation. Okay, we can explore the correlation. In K-mean we were not able to do our unsupervised classification. When we were using K-mean, we were not able to explore the correlation part of the data. But now here, this is the distance. Mahala nobis distance. Okay, and this distance has the quality to explore the correlation between the data. Okay, and which is present in our exponential part. Okay, so if your value is close to the mean of the density of the model, we say the density is large. Okay, and if x is far from the mean of your density, then you have a narrow density because you don't consider those points. Okay, so this density terms tells you three things: to scale your variables, okay, the distance, then the correlation among the units inside your data, and the orientation of your new class, so the location. Okay, how is your new class? So this distance explore if you have other shape of cluster without sphere. So it gives you the orientation, whether my new cluster is tilted to this side or it's tilted to this side. Okay, so you get also the orientation from here. And okay, so our first assumption was to use this Gaussian assumption, but LDA, this not enough, just this assumption. We also assume that the covariance matrices, all of the covariance matrices for every class is equal. Okay, so they have the same covariance matrices. Okay, so you have one class here, one class here, one class somewhere else. All these classes will have the same covariances. So this class will have its own covariance, but this covariance will be equal to the covariance of this class, and this covariance will be equal to the covariance of this class. Okay, this is assumption. Okay, and this is the assumption which helps us then to draw a clear boundaries. Okay, because we know the covariance, we know its fixed shape. Once we know its fixed shape, then we can draw the line. Okay, so to summarize what we are doing here, our problem is classification, and we are in supervised classification. We have labels. So the first target is for each point, we calculate the posterior probability. Then we shift to Bayes rules. with the help of Bayes rule, we use the densities and the posterior probability to assign new point to a particular group. Okay? So classification here is built by modeling the class density. What kind of density a class has. Okay? In the first case, we say, okay, our assumption was it's multivariate Gaussian. And then our final assumption was that each class will have the same covariances. Okay? Okay, so we know if they have the same covariances, this means that the classes will have the same spread, the same shape, the same orientation. So geometrically they will have the same shape, and that's the beauty then to distinguish between one class and another, to draw the line. Now, normally we apply, okay, if let's say we have two classes, class K and class L, and we want now to compare these two classes, to classify them. So how we do? We have the posterior probability for class K, posterior probability for class L. First we find the ratio between them, okay? But normally it's better to take the log of it so we can preserve the values, okay? The comparisons. We take log of them. When we take log of them, our mathematics kind of becomes easy, okay? When we take the log, then dealing with the exponential term is a bit more easy. So in the algebra and everything becomes simpler. So we started from Bayes rule, from Bayes theorem. We said the probability that X belongs to a particular group G is this: density posterior pi k, how much this point belongs, how many times this point occurring in that particular class. Okay, now we are comparing two classes. So probability of this, probability of this. This turns out to be fk this divided by this for class L. Okay, and these two cancels out. Then take the logarithm for both classes. So we apply logarithm here. So the rule of logarithm, applying logarithm to product becomes logarithm of A plus logarithm of B. So we apply that rule, okay? So now we can see here the comparison between two classes, K and L, has two parts: the density part and the prior probability part. Okay? Now, under linear discriminant analysis for class K, we will have something like this. Okay? For class L, we will have something like this. And we assumed before that the variance is the same. So when the variance is the same, this term and this term factors out. Okay? These two terms factor out. We left with this now. Now expand this exponential term. Okay? We do some mathematics. X multiply with this, multiply with this. Okay? First term, this, we get this. Then do the rest of other multiplication, we get this for the class K. Similarly for class L, we have this. The key fact to note here is this term, the first term, this one and this one. This appears in both expressions, in both classes, in class K and in class L. Okay? And it will cancel out when we are doing the comparison. So A class K minus class L, these two terms, this one and this term all factor out. Okay? If this factor out, this is the quadratic part. This quadratic part will cancel out and remains in the linear discriminant analysis again. Okay? Now again, apply log to this. So we apply log here. The rest of the terms are constant. Okay? And the only term we have here that involves x is this one. So this term involves x, which is a variable we want to know whether it belongs to which class. The rest are constants, okay? So we have a linear function. Yeah? So for class K, we have this. For class L, we have this. And to do their comparison, we take the log ratio. We said it's equal to 0. And this is that line. That line where we want to discriminate. Okay? We want to know that line. So this equation gives us this line. Whether it's a linear line or it's 3-dimension, 4-dimension, or in hyperplane, even a hyperplane for us could be a discrimination. Okay? Okay. I don't want it to make you more sleepy. Okay, final thing I want to show you before. So similarly, this is like we have linear discriminant analysis, we can have quadratic discriminant analysis where we don't have then the linear line, we can take curve lines, okay? But the idea is the same, to find the density, the prior probability, and based on that we find this line, okay? But then we have another technique which is called Fisher view. Okay, this is another direction for class separation. So the idea here is, instead of starting from probabilities, instead of working with probabilities as we were doing before in LDA, Fisher asks to work with geometric scenarios. Okay, and he says, can we project the data? So that idea now, okay, that's what is widely used. And that line in this case is this ATBA, okay. So here this is like the between class variation between two classes, okay. So what Fisher is saying, okay, forget about probabilities. We find this ratio. The ratio between two classes divided by the ratio between within class. And then we project. And this gives us the class separation. Between this, so we have to find this mean of the second minus mean of the first, mean of the second minus mean of the third. Okay, so here is the best example you will find in literature, which is, for instance, we have this data and the data is to make a separation between dogs and cats. Okay? So normally when we are doing PCA, you can say, okay, maybe this is PCA 2, PCA 4, coordinate 2, coordinate 4. But what Fisher is saying, to discriminate and have a clear discriminate line between dogs and cats, is to project these. Okay? So I can have maybe many axes. So if I project this data in this direction, I have the green and the magenta, the green color and the magenta. You see, when I project it here, it's kind of very overlap, the two distributions, the two densities here. Okay, so it's a very poor discrimination. So this line is very poor. Okay, but instead, if we project the dogs and cats here, what we have? Now we have a clear discrimination here, right?
If they have overlapping, so it means poor discrimination, they are looking separate source of dual projection.
Yes, yes. But even here, if you look, okay, you cannot have a perfect 101% discrimination. It's not possible because you have these tails. So there must be something, but at least you have a clear valley here. You can discriminate. So this was the idea of Fisher. Okay, Fisher said we need to maximize this distance, this ratio. Okay, and this ratio gives us what? This line, this discriminated line. Okay, so we need the maximum value here. And how we can get the maximum value here? If the separation between two clusters, if this value is big, if between two clusters this value is big, means the numerator is big, and if this value is small, okay, if this value is small, meaning this is what? Within cluster variations. If this is small, the cluster is compact. So we want this value in the numerator to be large, and this value in the denominator should be small. Then we can have a clear line of discrimination between the two classes. Okay? So this measures like the difference between two clusters, and this measures how individual cluster is spread. Okay? So individual cluster we want as compact as possible. Okay? And between two clusters we should have a maximum distance. So this is what the idea of Fisher. Okay? Okay, we finish here, and we're still working on the devices. I hope we could start it from tomorrow. In any case, if we finish working on it today, maybe I will put some news on the GitHub page. So have a look to GitHub if we can manage to work on the devices tomorrow. Otherwise, next week, next week we shall start from Thursday, and next week we do logistic regression. Okay, so see you tomorrow in the lab.